In this video, we're going to be connecting an STM32 microcontroller to an SDRAM memory interface IC. We're going to be looking at both hardware and firmware aspects, and then finally writing our own little test firmware to verify that we can read and write this SDRAM IC. Thank you very much to Altium for sponsoring this video. The board you saw at the beginning of this video and the one we'll be testing the SDRAM in combination with the STM32 microcontroller was entirely designed using Altium Designer. And if you'd like to give Altium Designer a try for yourself, make sure to check out the link in the description below or go to altium.com/yt/Phil's to get yourself a free trial. A huge thank you also to PCBWay for sponsoring this video. The boards you saw at the beginning were manufactured and assembled by them. If you're interested in the hardware design behind this board and the decisions for using certain components and how the circuitry is connected together, as well as the PCB design, make sure to check out my video number 78 on the channel titled Mini 6-Layer Mixed Signal Hardware Design. And that also guides you through some of the PCBWay ordering process, things to do with control impedance, specifications, what files you need to produce, and so on. This is the specific SDRAM IC I ended up using for this design. It's from ISSI. It's 128 megabits, so that's 16 megabytes, running up to 143 megahertz. Although for this STM32H7 I used in this design, I can't run the clock at 143 megahertz. I have to be below about 100 megahertz. Nice thing is this runs between 3 and 3.6 volts, so I'm running at 3.3 volts, and it's a 16-bit wide data bus, and it takes up to 100 milliamps maximum current. And we have various timing parameters which will be important when we look at the firmware setup later on. This is a 54-ball BGA package. You can also get them in a TSOP, but I thought it'd be cool to use this BGA, and it isn't too fine pitch anyway. We'll need to use these datasheet parameters, as I said before, later on in the firmware setup, but it's interesting to see the internal structure of these memories. I've also then, of course, used the datasheet to create my footprint and my symbols as well. I won't be going into terribly much detail on how SDRAMs function or how they work, what specific pin functions they all are. I'll provide a fairly broad overview. I can highly recommend the FPGAforfun.com website, and in particular the SDRAM section, which describes static versus dynamic memories, DDR and SDR memories, which we'll be using in this video. It'll go through how one might write even a controller for one of these memories, how the pins work, the structure of these memories and so forth, and it's a really great read if you're not familiar with these types of memories. For us as PCB and hardware designers, for now it'll suffice just to know the basic pin structures and functions and pins of an SDRAM. So here I am in this project schematic and in particular the memory section. I've chosen a 16 megabyte ISSI memory. ISSI is the manufacturer. They have various different specs. You can choose different clock frequencies, different row and column numbers, sizes, and so on. The most important factors are how much space you want, and that will determine the number of address bits you have, and how wide your data bus is, and as well as your clock frequency, or your frequency at which this SDRAM, this single data rate memory, runs at. I've chosen the 16 megabyte memory because for my purposes I don't need particularly much more. We can see we have power pins at the top, we have VDD, which is kind of the internal logic voltage, and this chip happens to run at 3.3 volts. In comparison to DDR memory, double data rate memory, SDRAMs typically can run at a higher voltage, such as 3.3 volts, whereas DDR2, DDR3 will run at half that, if not even lower. I have VDD as my internal voltage, and per VDD pin I provide 100 nanofarads of local decoupling, as well as for the whole VDD bank, so to speak, I provide 2.2 microfarads as my bulk decoupling capacitor, and we'll see later how these will be placed. I also have VDD-Q pins, which are my output driver voltages, which supply my output drivers. Again, per pin I have one 100 nanofarad decoupling capacitor and a 2.2 microfarad bulk decoupling capacitor. You might be wondering why we have two separate VDD banks, so to speak. The drivers, as the name suggests, drive the output. On the left-hand side, we have essentially passive inputs, and on the right-hand side of this symbol, I've laid it out, so we have outputs. On the left-hand side, we thus have all the address, command, and control signals, as they're called. So we have the address pins A0 to A11, so it's a 12-bit wide address bus, and this can be higher or lower depending on the memory device you choose. We have two bank address pins, as well as various command and control signals, as well as clock signals. I'd highly suggest you look at the FPGA for Fun website for detailed explanation of these pins. But these pins are essentially all driven by our host or our controller, which in our case is an STM32 H7 microcontroller. So these pins are all inputs. On the right-hand side, these are the driver-based pins, which are outputs as well as inputs. So when I want to write to this memory, I will provide an address, I'll set all these control and command signals, then I'll place logic signals on these data lines. On the other hand, if I want to read, again, I will provide an address, set my command and control signals appropriately, and then this memory device will output and drive the data signals. For driving, I then need to use my driving voltage VDD-Q. If we look at the I/O signals of this data line, we have DQ0 to DQ15. So this is a 16-bit wide data bus, and again, this can vary depending on your needs. Of course, if we have a higher data bus width, we can transfer more data with a single clock cycle. Our data pins can be subsectioned into byte lanes. For example, byte lane 1 is, or the lower byte lane is DQ0 to DQ7, which is 8 bits or 1 byte wide. And then we have our second byte lane, our high byte lane, which is DQ8 to DQ15, again 8 bits wide. I also have corresponding low and high data mask signals which correspond to the byte lanes. Now within the byte lanes, it can really aid routing because we can do bit swapping. So DQ0 doesn't have to route to the STM32's DQ0. We could switch these around within the byte lanes if this makes our routing life easier. So this is really useful. And you can see this a lot also in DDR memories. In Altium Designer, I've then placed these blankets and directives and given these net class names to make sure I route the address, command, and control signals with similar timing, as well as my individual byte lanes with similar timing. Other than that, I just have a couple of ground pins, and that's pretty much it. On the microcontroller side, I simply have hooked up relevant pins, my address, command, and control, as well as my data signals. And I'll show you in just a second how I got the pin out for this. You might also be wondering that there's no termination or no termination resistors on any of these RAM lines. And this is because when we look at the routing and layout later on, I've placed the RAM device so close to the microcontroller that the trace lengths are so short that we really don't require termination. Also in combination that this RAM is running at a fairly low speed. As usual, I like to do my pinouts for STM32 microcontrollers using STM32 Cube IDE, which is the free integrated development environment provided by ST. Here I can create a project and then create my pinout, and if I go to connectivity, I can click on FMC, which is my flexible memory controller, and I've selected SDRAM 1. I could have also selected SDRAM 2, but because I have quite a lot of other peripherals connected to this STM32 H7 microcontroller, I had to ultimately go with SDRAM 1. I then select my clock and chip enables and various other parameters such as how many address bits I have, which happens to be 12, and how many data bits I have, which happens to be 16. I have to enable the byte enable and the clock and chip enables, and that gives me my pin out. I can move certain pins around a tiny bit, but this is pretty much fixed. So I can then see pins of my address lines, maybe my data lines, and so on. And this is what I've then transferred into Altium Designer, my ECAD software, to do the pin out. Now we do also have further parameters, which we have to set up when we come to the firmware section. But first, let's look at the PCB layout and routing. Next, looking at the PCB layout and routing quite briefly, there isn't too much to this in this design because I've managed to keep the space between the microcontroller and the BGA of the SDRAM fairly close to each other. Now this was a fairly space-constrained design, and this is a two-layer assembly board. So there's the top layer with the STM32 microcontroller in the center, and on the bottom layer I have this fairly small BGA SDRAM IC. Now normally with a BGA I would place my decoupling capacitors on the other side, with vias then connecting with short white traces to the pads of this BGA. However, because on the other side I do have a component, I can't place any decoupling capacitors there, so I've placed my decoupling capacitors fairly close around the perimeter of this IC. In 2D mode, I've then tried to place my decoupling capacitors close to the perimeter and close to the pins where we have 3.3 volts and ground, which happen to be located also along the perimeter. But some of these are also underneath or in the middle of this IC, and that's why I've used fairly wide power poles to connect then to my decoupling capacitors on the other side. I have internal ground and 3.3 volt planes, so I then also use closely spaced vias to dig down and use some of that interplanar capacitance. Now, not only because of the space constraints, but also because it made sense routing-wise, I've placed this BGA SDRAM right in the center and underneath my STM32 microcontroller. This is because the address command and control, as well as all of the data signals, are all along the perimeter of this microcontroller. This way I can just route underneath, dig down and into my BGA. And thus, because I'm routing fairly equally along each perimeter side, I'm getting very closely matched traces. In essence, I actually didn't do any length matching because the traces are fairly similar anyway. It is slightly annoying to root out SDRAMs or DDR memories, but for this SDRAM I didn't pay too much attention to it. I essentially rooted out as easy as I could, dig down to the top side, and then routed into the microcontroller pins. If I go to the PCB filter on the left-hand side, you can see I've got my net names for the address command and control signals, and we can see the delays for those, and they are ranging from 53 picoseconds up to about 155 picoseconds. So a tolerance or difference of a maximum of about 100 picoseconds, again because I've placed the ICs in a specific way. The same goes for the data byte lanes high and low. In this way, I've made my routing life really easy. I didn't really have to care about length matching, especially not at these speeds. Now let's move over to the firmware setup, and I'll take you through the setup of the FMC and our clock configuration. In your project configuration, go to FMC and then enable whatever SDRAM bank you would like. I've chosen SDRAM 1 because this was dependent on the pinout and all of the other peripherals I'd chosen. You want to select your clock and chip enable, and I've chosen clock enable 0 and chip enable 0. The internal bank number is dependent on the size of the memory. I have a 128 megabit memory, so I need 4 banks. Then we have the number of address bits and the number of data bits. From the datasheet, again, we can see we have A0 to A11, which means we have 12 address bits total. And we have DQ0 to DQ15 on the right side here, which means we have 16 data bits. So in STM32 CubeIDE, I have 12 address bits and I have 16 data bits. And I've also selected that I have a 16-bit byte enable, which essentially are my byte data masks. So data mask low and data mask high. You can see this STM32H7 actually supports up to 13 address bits, but we're only using 12. So this alone will already give you your pinout for your FMC, so where all of your address bits are, where all of your data bits are, and all of your control signals and so on. However, we also need to do this setup in the configuration window below all of this. The first thing we have are the number of column address bits and row address bits, and this again we take from the datasheet. We can see we have a row address latch with a number next to it, and that's 12, so that's the number of row address bits, and we have a column address latch with the number 9 next to it, which means the number of column address bits. This is what I then put over here, so 9 column address and 12 row address bits. The cache latency we have to select depending on what speed we're running this device at. Again, look in the datasheet on page 1 even, we have the key timer parameters. This depends on the speed grade, it depends on what your processor, your host can handle, and so on. I can only run below 100 MHz, and it happens that I have speed grade 7, which with a cache latency of 3 runs at 143 MHz max, and the cache latency of 2 runs at 133 MHz max. I'm actually running below this, so I've chosen a cache latency of 2. Again, here we go, 2 memory clock cycles, my cache latency. Write protection I've left as disabled, and now we have the SDRAM common clock, which I've put at 2 clock cycles. You can also choose 3 clock cycles. Let me show you why I've chosen 2 clock cycles. In my clock configuration tab, you can see I'm running my core of this STM32H7 at 550 MHz, which is the maximum for this device. If we scroll down, we have an FMC clock, so to speak, and I've selected that to be 190 MHz. Remember, for this STM32H7 from the datasheet, I saw that I can only run the attached SDRAM clock at less than 100 MHz. I'm actually running it at 95 MHz, which means I have to divide 190 by 2, and again, this means I need 2 clock cycles here for the common clock. Essentially, I'm dividing down my FMC clock in the clock configuration tab down by this factor, in this case 2. So I'm running this memory at 95 MHz. I've enabled the common burst read, and I've set the common read pipe delay to 2 clock cycles. Now comes somewhat of a confusing part. We have to specify all of these timing parameters here. For example, exit self-refresh delay, self-refresh time, and so on. And these have to be rounded to the nearest integers in a certain way. We can get this information by looking at the datasheet at the AC electrical characteristics, and we have a lot of these timing values. And depending on the speed grade and so forth you use, you'll have to enter these in. I won't be going through this in detail in the video because the calculations are a bit annoying and a bit long and tedious, but I'll leave a link to this article by ST in the description below, and this is exactly what I used to then calculate these values. And specifically in section 5, setting up the SDRAM timings, I've just followed this guide. It'll guide you through exactly what you need to know, how to round the numbers depending on various factors, speed, grades, and so on. So I've just followed all of this guide, and these numbers I've then entered in the SDRAM timing down here. And this will be device dependent to which SDRAM you choose. Once you've done that, you're pretty much good to go, and you can save the project to generate the code. Once the code has been generated, if you're using the hardware abstraction layer provided by ST, in main.c and in main, we have our usual initialization functions, and as well this mx_fmc init function, which initializes the FMC peripheral. However, unfortunately not quite all of it, and we have to add our own code. Down below, I've added my own custom function fmc_init. If we go up to the function declaration, this code we have to copy in. And this is something I took from the article I previously mentioned, again linked in the description below, and you have to modify that slightly depending on your use case. What I had to change is this reference here, so if you're using bank 1 or bank 2 for the SDRAM, you have to change 1 and 2 respectively here. Same goes for command target. If you're using bank 1 or bank 2, you'll have to change that here. I'm using bank 1, so this is fine. One thing that you do also have to change at the bottom here is the calculation of the refresh rate counter. Essentially, it's the SDRAM self-refresh time divided by the number of rows times the SDRAM clock. I'm running at 95 MHz, and these parameters are essentially given in the datasheet. From that, we have to subtract 20 and then essentially round to the nearest integer. So I get a value of 1464. Again, this was in the guide I showed you previously. Once we've done the mx_fmc init, and then we've also initialized the SDRAM with this function, we are pretty much ready to test our SDRAM. I've now hooked up my ST-Link V2 via the Tag Connect 0-wire D-wire probe to this board, ready to be programmed. We're now ready to write some very basic test firmware to test this FMC controller as well as the SDRAM to see if we can read and write some basic data. We'll also do a small little speed test to see how long that might take to read and write data. For STM32 devices and for the FMC controller, the RAM and the memory is memory mapped. This means that our SDRAM bank 1 and bank 2 will appear at certain addresses in the STM32's memory space. We can then simply use pointers pointing to a certain bit of memory to access the SDRAM to read and write. To find out where this memory map is or what location in the memory this SDRAM is mapped to for certain banks, we need to consult the reference manual of the relevant device we're using. I happen to be using an STM32 H723 device, so I found the relevant reference manual for this. And this is quite a chunky bit of documentation at almost 3,500 pages. However, if you scroll down to page 831, looking at the external device address mapping, we can see we have the FMC memory banks as well as addresses for the relevant memory maps. We are using SDRAM bank 1, and on the left-hand side, we can see that the start address of this SDRAM bank 1 is at OXC followed by 7 zeros, and extends all the way to OXC followed by 7 Fs in hex, so we get 4 times 64 megabytes. Of course, we're not using all of that for our device, but in theory, you could address this much memory. If you were using the second SDRAM bank, your start address would be OXD followed by 7 zeros. However, our start address is at OXC followed by 7 zeros, and this is what we need to use. So by simply pointing, for example, to this start address or anywhere in this address space, which is in the bounds of our memory, so in this case, or in our case, 128 megabits, 16 megabytes, we can read and write using pointers, for example. You could also use memcopy or a similar function, but that requires including string.h. Thus, if we go to our firmware, in my main.c file, I've defined the SDRAM start address, again from the STM32 memory map at OXC followed by 7 zeros. I've also defined the SDRAM size because I'd like to start at the SDRAM start address and loop through until my maximum number of bytes, and I've just written that in hex. Then I've written a very small, simple little test function. Essentially, there's 2 stages to it. One is to erase the SDRAM memory, and one is to write essentially incremental data to the SDRAM memory. Later in debug mode, we can use a very useful tool called the memory monitor to see what changes are reflected from start address OXC followed by 7 zeros, and so on. So in that way, we can read through the debugger what's happening with the memory. and this lets us verify the contents. Let me just go through the function very quickly. We also have FMC test start and stop variables, and these are just containers or variables to store the current tick. HAL get tick returns the current system time, so to speak, in milliseconds. So by doing a start tick and then a stop tick and taking the difference, we get the runtime in milliseconds for that certain for loop, very crudely. For loop, I'm starting at a counter, and I'm running this counter for the whole size of the memory, incrementing byte by byte. Then I'm simply using a uint8t type pointer, so a 1 byte pointer, starting the base address and adding to that the counter. So I'm starting from the base address, incrementing byte by byte until I reach the whole end of the memory, and simply setting that pointer location to 0, so erasing the memory. The second test is very similar. Again, I'm checking the time it takes to do this with FMC test start and FMC test stop variables. I'm looping through the entire memory and just essentially writing the counter directly to the variable, directly as a byte. The uint8t variable will of course overflow, but it's just to see through the memory monitor that we are writing some form of data to the SDRAM. In int main, we have our usual HAL setup, our FMC init function, which is auto-generated by STM32 Cube IDE. We have our own FMC init function, which we had to add, and then I call the FMC test function straight after. I have my device connected via serial wire debug, so I can click the little debug icon at the top and load the program into the STM32 microcontroller. In my FMC init function, I've just set a small breakpoint to check the status after we do HAL SDRAM send command, and the program I can resume then. And we can check the status is HAL OK, so that's already a good sign that we're getting something back from this HAL SDRAM send command, which is an error or so on. So that's always good to check. Next, in the FMC test function, I'm setting a breakpoint just after we erase the SDRAM memory. In the middle tab at the bottom, we can see this memory tab here. Let's click on that. Click on the little plus. Now let's enter the start address of our SDRAM memory and click OK. This lets us very easily via the debugger see what the memory contents are at certain locations. So remember OXC followed by 7 zeros, the start address of our SDRAM, and that runs through for 16 megabytes. Currently, there's nothing or gibberish in there because we haven't accessed this yet. So let's fill the SDRAM with all zeros, check out the time and see what happens to the memory monitor. So let me click resume. After a short amount of time, we can see the memory monitor has updated, and starting from OXC followed by 7 zeros, we have all of these zeros, so we've erased or cleared the SDRAM, so to speak. Of course, I could scroll through 128 megabits of data, but you get the point. Looking at how long this took, I can hover over the FMC test stop variable, and that was just about 305 milliseconds, or 0.3 of a second, to clear 16 megabytes of data. So that's pretty cool. It verifies that at least we can clear and access the data on that memory space. That's promising. Now let's look at the write function, which essentially writes fairly incremental data with overflows, of course, to the various bytes of the SDRAM. I've set a breakpoint again afterwards so we can check out the time. Keep your eye on the memory monitor as I click resume. There we go. Looking through again from the start address, we can see we have, fairly incremental data the way we've written this code over here. So we're storing some sort of data into the SDRAM. So that looks pretty cool. Let's look at FMC test stop, and that's at about 400 milliseconds now, so 100 milliseconds longer it took to execute this code. But this looks like our SDRAM at least works. We can access it via memory map. We can store some data in a fairly short amount of time. So 300 milliseconds to erase 60 megabytes of data, 400 milliseconds to write 60 megabytes of data, for example, in this very crude implementation. Thank you very much for watching this video. I hope it was helpful in showing you the basic connections for SDRAM and then how to interface that with an STM32 microcontroller, both in hardware and in firmware. If you haven't already, please make sure to subscribe. I try to post about a video a week on various topics on DSP, PCB design, electronics, and so on. Thanks again for watching, and I hope to see you in the next video. Bye bye.